Let's see, so we want to look at piecewise linear interpolation. Okay, now interpolation, that part is just that, you know, I have some data, some points here, something like this, say, and interpolation just says that I am going to find some sort of function that passes through these points. So, you know, if I did, you know, if it did not contain the points, I wouldn't have interpolation. So whatever I come up with, I need to have the points as part of the function. Now, linear part, all right, well, it's a straight line. And so that straight line connects those points. But of course, you know, these points are not in a straight line, and that's the piecewise part. And so we're just going to build a piecewise function on this thing. Now the way that the notes that I gave you to look at work, they would have this as, well, make it an x, x1, x2, x3, x4, x5, something like that. So, and here equals 5 points. And that's fine. It's possible at some point I will start with x0, but x1 is fine for a starting point. And then in the notes it mentions, you know, these points here, we could call them just y1, y2. They call them f of x1, f of x2, and so forth. Either one is fine. So we can go with f of x1, f of x2 is that height there. These are the heights, and so forth. So, you know, I go to f of x5, f of x, oops, 4, and f of x3. So, you know, what would happen, right, is more likely you'd have this data. You know, maybe you'll have something like that. You have x1, x2, x3, x4, x5, and then your f of x1 or y1, f of x2, f of x3, f of x4, f of x5. Now, to create our piecewise linear function in here that we're going to call p, in your notes that's p, because it's a interpolating polynomial. It's a polynomial of degree 1, but it's a interpolating polynomial. What we won't get into in this class are lots of different ways we could use polynomials to interpolate. I think we'll just, you know, I think you ought to consider what interpolation is, and we'll just do piecewise linear and see how we could do that. Partly because I think to think about creating line segments is a very good thing to know how to do. And so we want to create that first line segment, and we'll maybe call that P1 of x. And P1 of x, well, I've got 2 points, right? I have my x1 f of x1 and x2 f of x2. Well, I can just use the point slope form. You are used to most likely, thinking about y minus y1 equals m times x minus x1, where m equals, and whoops, we've got, say, a y1 minus y2 over x1 minus x2, something like that. And all we do, and all the notes do, is they move the y to the right side of the equal sign. And yeah, I mean, you're trying to set up a function, and I think there are reasonable reasons to introduce this y minus y1, but in the end, that's poor notation. And so we want the y1 on the right side. And partly also because when we do that, this starts to look like a Taylor series. And so we've got a Taylor polynomial. And you all have seen Taylor polynomials. And so a Taylor polynomial starts out at some given x. And now we could use either x1 or x2. It doesn't matter. I'm going to go with x1. That's what I believe they do in the notes. So we'll have x1, then plus f prime of x1. Oh well, we don't have a derivative. We just got these points here. Well, we can approximate the derivative with the slope, and so that's f at x2 minus f at x1 over x2 minus x1, and then times x minus x1. And there you go. And with our approximation of the derivative for whatever this unknown function is that we have points for, this is a first order Taylor approximation, and that's all it is, right? And so we're just using this point slope form. And so there's our P1, and similarly we could do a P2 with x3 and x2 and so forth. So we're going to need 1, 2, 3, 4 pieces of polynomials to connect these 5 points. And so if I come down here, I'll have a P2 of x, I'll have a P3 of x, and I'll have a P4 of x. And each of these, of course, is just on this interval from x1 to x2 or x2 to x3 and so forth. So, if we have something like, here's x, here's our f of x or y, and maybe this is 1, 3, 4, 7, and 8, something like that. We have those points, and then here maybe 5, 10, 8, 9, and 12. So we have something like that. Then I can actually make each section. So P1 of x is 5 plus 10 minus 5 over 3 minus 1 times x minus 1. And that is for x between 1 and 3, whoops, x less than, and I'll use a strict less than there, I guess. And then I have P2 of x, which is 10 plus 8 minus 10 over 4 minus 3 times x minus 3, and that goes from 3 to 4. and then P3 of x is 8 plus 9 minus 8 over 7 minus 4 times x minus 4. And so that's 4 less than or equal to x less than 7. And then finally, P4 of x is equal to 9 plus 12 minus 9 over 8 minus 7 times x minus 7. And that's from 7 to 8, and I'll put an equality on that last 8. And so now I could write this as a single function if I want. So P of x equals. And, you know, oh, that sort of looks maybe person-ish. Maybe that's a nose. And it's a really big chin and some lips. Put some eyes up there. Okay, so here, if I simplify this, this is 5 plus 5 halves. So I get 5 plus 5 halves x minus 1. And again, that was from 1 to 3, so less than or equal to x less than 3. And then we had 10 plus negative 2 times x minus 3. And that was from 3 to 4. And then we had 8 plus 1/3 x minus 4. 4 less than or equal to x less than 7. And then finally 9 plus, what do we got, 3 times x minus 7. 7 less than or equal to x less than or equal to 8. There we go. And there is our piecewise linear interpolant for those data. And that's all there is to it. We're just finding that that function somehow. There are other ways to do it, but you know, this will work. They did mention parameterize function. Let's go ahead and oops, I need to do that. Okay, so the other way to look at it is if I have it, oh, I got to go back here and find a couple points here. Okay, so what we have here, we had 1, 5, and 3, 10. So, you know, I have these points 1, 5, and oops. Oh, I'm way down here. That's kind of weird. Hit the eraser, get rid of that. Okay, we'll go up to the top. Okay, we had 1, 5, and 3, 10. So another way you could do this is you could do it in terms of a parameter t, and so what you're going to do is take what we call a convex combination of all points in between here, and it's pretty much, it's a convex combination from 1 to 3. So, you know, we're going to do something on the x in the x direction and something in the y direction. And so what we can do is and you can look at this as a whole point or something like that. So I could take my point and my 2 points and say something like, oh, okay, well, and what's neat is I can decide which one I'm going to start and stop at. Say I'm going to start at 1, 5 and stop at 3, 10. Then what I would do is, you know, I could say it this way, 1, 5 times 1 minus t plus 310 times t, and that's for 0 less than or equal to t less than or equal to 1. And notice that if t is 0, I get 1 times the 0.15, and 0 times this point here, 310, and so I just get 1, 5. If I have t equal 1, I get the 310 here, and then I get things, everything in between, and it is a straight line. So, so it's parameterized, or in other words, I've got that x is equal to 1 times 1 minus t plus 3t, and I have that y is equal to 5 times 1 minus t plus 10t. And here we're saying 0 is less than or equal to t is less than or equal to 1. So, my claim is that for any t in that range, we get numbers that are between, for x, 1 and 3, and we get numbers between 5 and 10 for y. And you could, check that out. And then the other claim is that for any of those numbers, this relationship is a straight line. Well, so how do you check that? Well, you have to go and solve for t in one of these. And, so if I do that, I have that x is equal to 1 minus t plus 3t, but that's just 1 plus 2t. So x is 1 plus 2t, subtract 1 and divide by 2, and I get that t equals x minus 1 over 2. Now, if I plug that in for y, you see I get y is equal to 5 times 1 minus t, which is x minus 1 over 2, plus 10t, so 10 times x minus 1 over 2. And you see that it's pretty plain that this is going to be linear, because I'll just get a minus 5x here over 2, and here I'll get a 10x over 2, right? But there's no x squared, it's nothing like that. And so this is linear. I can write this out, so 5 minus 5 halves x plus 5 halves, and then plus 5x and minus 5. So let's see, 5 minus 5, those go away, and so I get 5 halves x plus 5 halves. Linear, right? Y equal mx plus b. So, this is another way to do each piece. So between, any 2 points, I can string that line segment simply by taking 1 minus t times one of the points and t times the other point. And wherever I put the 1 minus t, that's where I started, and where I put the t is where I finished. Okay? So that's just another way to come up with that formula. It's nice parameterization. Alright, so that's linear interpolation, or piecewise linear interpolation, and we'll call that one done.